Okay, so I was asked yesterday by Michael and then coerced by Adam to give a talk sort of around my PhD stuff. And so this is like an amalgamation of like 3 talks, which is way too long, and so I'll go super fast. And so what I'm trying to do is give a tiny bit of an overview of what geophysics is, why it might be useful, and sort of how, like what sort of things 3point could get out of it. So this is sort of a talk on working towards all the geophysics, but backwards. And really it's a talk about some of the geophysics with really working with sort of a multidisciplinary team behind it and sort of increasing the communication in geoscience. So, as geologists, geophysicists, geoscientists, we're sort of interested in what is going on under the ground. So this is what Leapfrog does. We like create models of the subsurface. So we don't know what's under there, so that we have a couple options. We could dig it up, we could just actually excavate the whole thing, or we could put some pipes into the ground, so drill these things and maybe figure it out that way. And so this is really what Leapfrog does, is they have drill holes that they poke into the ground, and then they interpolate surfaces through that. Another way to get at what's under the ground is to light it up through some sort of geophysical method. So you create some source, some explosion or electromagnetic pulse out here, and then it interacts with the subsurface properties in some way, and then you record some sort of data at there. And so the idea is that given this data and knowing something about the physics, we can figure out what the physical properties are, which would tell us something about the geology. So the world's in 3D, and so this gets a little bit more complicated. So some of the methods that people go out and collect are gravity. So you'd like go out into a survey and you'd like have your spring, very sophisticated spring with a mass on it, and you'd be very sensitive, and then it would go over some part and maybe there's less stuff under the ground there, so you would be sensitive to that. You could go out with a fancy compass, and you could measure some sort of magnetism under the ground. Or you could hook up a battery to the ground, inject current in one side of this, goes through the ground, and then you have all of these voltmeters that you sort of measure what that looks like. You could use seismic, so this is what Brendan spent his PhD doing. So you set off some explosion, you have waves, and then you set a bunch of receivers out there. Or you could use magnetotellurics, which is sort of waves, electromagnetic waves that are just sort of in the atmosphere that we can measure the ratio between the electric and magnetic sources to figure out what's going on. So I guess one of the pieces that UBC was working on a lot was this case study up in Northwest Territories called TKC, which is sort of a prospective diamond mine. And so this is actually the 3point software running in the background that we were using to do an interactive meeting around this. And so just as I want to go through this again quickly with some other pictures. So maybe you go out, you collect this gravity survey, and then you get this map of sort of where the low density stuff is, where the high density stuff is. But this is just your data, so this doesn't actually tell you directly about density, so you have to sort of back propagate the model out of here. So you look at some sort of, so going from your data to try and sort of infer the physical properties, and so you recover some sort of density model about the Earth. But this isn't going to be like an awesome picture of the Earth because you only have 2D data and you're trying to infer a 3D distribution of properties. And so from this, we can sort of like make some sort of interpretation of this and put a circle on it, and then we get your geology model out. So that's one method. You might go in there and you might do sort of another method. So magnetics tells you about something differently. So the physical properties of how dense something is versus how magnetic something is. We can just sort of do that same sort of interpretation, go through that step. This is called an inversion, to go from data to a model. and then interpret it in some way. And so now we're just sort of layering those things on top of each other. Maybe we'll do another one with direct current resistivity, pumping currents through the ground, or magnetotellurics. So really what we're getting at is that there's lots of different physical properties that are telling you something about the subsurface. And from this, we can then sort of interpret that. And so I was saying this was a prospective diamond mine. Well, we know that kimberlite, where that's like sort of the geologic lithology intrusion that hosts diamonds, so that by drilling it and knowing something, we know it's low density, moderate susceptibility, so moderate magnetism, and high conductivity, and so we can just sort of draw that out. And this is actually a synthetic model, so we knew what the forward, or what the physical properties were, so we're sort of testing our algorithms here. But this is in 3D, and so we need to communicate that, we need to be able to see all of these different methods, we need to be able to access them in some way. And then sort of where, that's really sort of where the science is. It's like we have these, all of the ability to do all of these methods separately. And then we can sort of lay them on top of each other, maybe do some fancy way of putting them together, but really in a quantitative way to put them together, that's sort of where we are right now as a field. I'm going to skip that. So this is like one way to look at this. There's like all these methods of like fluid flow over here, and then direct current resistivity, electromagnetics, magnetotellurics, potential fields with magnegrav, and then geology over here is they're interpreting that. They're sort of drawing some pictures, and they're doing RBF. For example, what LeapFrog does is fancy interpolation in a geologic way. So we go out, we collect some data, and from all of these different datas, we create a bunch of models, and sort of where science is actually combining these in sort of a more quantitative way. So using two methods at the same time to tell you what, like, a better model of the subsurface that explicitly fits both of those data sets at the same time. So this was, my PhD was actually initially focused on the sort of near surface flow side of things. So this is like the top 100 meters, 10 meters of the Earth, where you have precipitation above the groundwater and you have infiltration in there, and you want to figure out the physical properties of that, of the vadostone, which is what it's called. And so using direct current resistivity to figure out something with that. But it turns out that all of these methods, just because of the history of how they were developed, they're all sort of in silos. And so the communication, especially quantitative communication between them, is like really difficult to do. And so what my PhD ended up being was sort of doing all of these methodologies and sort of rewriting them in a consistent way. And so that means, yeah, so like how do you do that? But the sort of goal of this is if you had multiple data sets and you wanted to combine two things, you just sort of pick the methods, you put it together, you explore algorithms of how to quantitatively connect these things in a sensible way. And then you get out a model, hopefully, that fits both of those processes. So write it down, and then just start doing software at this point, basically. So take that framework, diagram, do a method, implement it, add another method, figure out if like your ideas still hold, what needs to happen to sort of change these things, add another method, work with other people, and sort of like the thing that you're trying to do, which is this geophysics framework for modeling inversion, is sort of getting constructed by like adding these things and sort of testing your assumptions along the way. And so we got to something which looks like this in the paper that we submitted, but it looks like this in the software that we've written to do this. And so this is like the class inheritance diagram of all of the geophysical methods that we've implemented. So it's like 250,000 lines of code written by like 10 people over 4 years, and then put all together and tried to figure out how this works in a sensible way. And so there is actually some structure in here, which is interesting to see. But like, I guess at some point, like, why would you even want to do this? And I think that, well, if you're organized about things, then you significantly lower the barrier to entry of mathematical equations. So like, if I gave someone this, that's helpful to a mathematician, but it's not helpful to an applied geophysicist. So you need to be able to translate the math into code, into physics, and that's much easier if things are organized, especially on the software side. And so if things are organized, you can give it to other people. So this is undergrads, this is using counterpoint conductor stuff that Michael's done to sort of like get this into the hands of students. So now they're running real geophysical tools in an undergrad classroom, which is something that used to take like a PhD to be able to do. So another thing is if stuff is organized and sort of quantitatively and like you've actually written it down in code rather than in a paper, which would be on this side of things, is like they have an algorithm, they want to tell the world about it, so they write these boxes and create a picture and send it to a journal, and that's helpful to some extent, but you can't reuse this, you can't interrogate it. Whereas if it's in software, you can do really interesting things with it, and so you can explore the algorithms, visualize them, see how they're connected. And you can start to add slider bars to these physical equations. And so this is sort of where what I've been pulling together over the past month is like a story around this. And so some of the applications that I've done is, so this is STEM 3D, or view, no, this was STEM 3D that made this picture. So creating, so this is like the top 2 meters of soil, seeing some heterogeneous sand and loamy sand, and doing fluid flow through that. So some of the stuff that Michael was just talking about in terms of visualizing time-lapse processes interactively in your browser, giving it to someone else, that's exciting, but you also need the physics to be able to generate that. Having some way to connect all of these methods together, and also exploring some of the ways to interact with geologic methods and interpolations and interpretations that are in a very different space than the geophysics. Cool. So, any questions? Lots of stuff.